In the last segment, we demonstrated the importance of having a measure of central tendency and a measure of variability to estimate the normal distribution. So in other words, if we have a mean and we have a standard deviation, we can model the normal distribution of the variable that we're measuring. In other words, the normal distribution of our values. Now we want to make sure that the underlying distribution is normal, and so we need to calculate what's called a skewness statistic. So in other words, is the data that we've collected, is it skewed or not for the underlying population? And so we'll use the formula SK, and this formula SK will give us a measure of skewness. Now I mentioned before that with any data we collect, it's never going to be perfectly normally distributed. It's going to deviate slightly. So what we want to know is it close enough for us to model a normal distribution. And so the skewness statistic will help us determine if our distribution if our variables or values are normal enough to assume a normal distribution. So we'll take mu, the Greek letter mu, so in this case for the population, the mean for the population, and we'll subtract the median. We will then divide that difference by the standard deviation, and we talked about the standard deviation already and how to calculate that. So we'll divide it by sigma, and then once we have that, we will then multiply by 3. So we'll take the mean, we'll subtract the median, we'll divide by the standard deviation, and then multiply that number by 3, and that will give us the skewness statistic. Once we have our skewness statistic, we then need to determine if our underlying variable is normal or if it's skewed. And so in order to do that, we will look at a skewness table. And in the skewness table, you'll see the symbol n, that stands for the number of observations, and you'll note that as n increases, or as the number of observations increase, the range for a normal distribution gets smaller, and that's because it's becoming more stable. The more observations we have, the more reliable our value, our measurement becomes, our variable becomes. And so in this particular case, we can see that it ranges from n's of 10 all the way to n's of 100 plus. Once we get to 100 plus, it stabilizes, it doesn't change much, and so anytime we have observations of more than 100, we use that very last interval of the upper and lower that's next to the 100 plus symbol. So let's go through an example, and so let's go ahead and use our communication majors data that we've already calculated. So if you remember, we had a mean of 42,500, we have a median of 42,000, we had a standard deviation of 6,700, and since we have all those numbers, we can calculate a skewness statistic. So we can determine whether or not our variable, in this particular case, salary for 2005 communication majors, if that population, if we can assume it to be normally distributed or not. And so we'll take 42,500, we'll take our mean, we'll subtract the median of 42,000, and then we will divide that number by 6,700. So we take 500, divide by 6,700, and then we take that number and we multiply by 3. Once we do that, we end up with a skewness statistic of 0.22. So now we want to take that skewness statistic and we want to compare it to our table. So here is our table. So in 2005, there were over 200 graduates for a communications majors degree. So we want to look up on our table for a sample size of 200, and you notice that there isn't one for 200, but we do have 100 plus. And so we'll look at that particular row, that second half of the row, and then we want to look at the lower and the upper limit for our skewness statistic. And notice that it's centered at 0. That if our skewness statistic is 0, then there is no skew, and we could say it's perfectly normal. So in this particular case, we had a score of 0.22 and indicated a slightly positive skew, but the question was it skewed enough for us to say it is truly skewed, or is it normal enough for us to say it's a normal distribution? In this particular case, a skewness statistic of 0.22 falls within or between our lower and our upper bound. So it falls between negative 0.37 and 0.37. If our value falls, our value for skewness falls between the lower and the upper bound, then we would say that it is normal enough. And so we'll assume a normal distribution. So in this case, 0.22 falls within a range of negative 0.37 and 0.37. And so we'll say that when it comes to communication majors salary, for the data we collected in 2005, we will say that that is normal enough. We will assume a normal distribution, Now in our example, we determined that our distribution was normal enough. But what if it wasn't? What if it was a skewed distribution and we couldn't assume that it was normal? Then what would we need to do? So we've talked about this before. We would need to make a correction. And so had our value fallen above our range of 0.37, so let's say we had a value of 0.5, then we would indicate, because it's a positive number, that we had a positive skew. And so in order for us to correct for it, we need to go back to the original salary data for the 2005 majors, and we would have to take the square root of each of those salary data for each of the graduates. We would then recalculate our measures of essential tendency and variability, and we go through the process again, and we check again for skewness to see if we had corrected for it. Now, what if our skewness statistic was a negative number, and a negative number greater than the lower bound of our range? In other words, lower than negative 0.37. So let's say negative 0.5. Well, that falls outside of our range in the negative direction. We would say that is a negative skew. And in order for us to correct it, we'd have to go back to the original salary data. And for each graduate, we would need to square each of their salaries. We would then, again, calculate our measures of essential tendency and measures of variability again, and then check for skewness one more time to see if we had corrected it. So it's an iterative process. We would continue to do that until we had a normal distribution. Now again, in this case, we had a normal distribution, so then we could continue with the remainder of our statistics that require or assume a normal distribution in the population.